In the next section in Chapter 6, we're going to discuss mechanisms and arrow pushing. So this is a very important topic for drawing organic chemistry mechanisms, which we'll see later all the way throughout this course. So as an example, we saw some arrow pushing when we discussed acid-base reactions in, I think, Chapter 3. So here we have an example of that. We have a base that is pulling a hydrogen off of an acid, okay, and then now we formed a bond from the base to the hydrogen, and the conjugate base of the acid is left behind, okay. So how do we do that? We have this base that has a lone pair and a negative charge. Sometimes bases don't have negative charges, but this one does. So that lone pair is going to attack, we say it attacks, this hydrogen on the acid and remove it, okay? So when it does that, the lone pair forms a bond to the hydrogen, and the bond is broken between the acid and the hydrogen. So the hydrogen and its conjugate, the acid and its conjugate base that was bearing the hydrogen, okay, that bond is broken. So we show the arrows like this. The tail of the arrow goes on the lone pair or bond that it's coming from. The head is on where it's ending up, okay? So especially in Wiley Plus, you've got to get this straight, because if you don't have your arrows straight, it's going to count it wrong. So for this example, the lone pair, the tail is on the lone pair, the head is on where it's going, and then we're breaking this bond. The tail is on the bond, the head is on where it's going, okay? So then this lone pair has become a bond over here between the base and the hydrogen, and the conjugate base has ended up with the lone pair that was in the bond. So this bond became a lone pair on the conjugate base. So there are four main ways that electrons move in these ionic or polar reactions, and we're going to see this over and over and over throughout this course. We have nucleophilic attack, loss of leaving group, proton transfers, and rearrangements. Okay, so we're going to look at each of those ways that electrons move throughout the rest of this chapter. So nucleophilic attack is a nucleophile attacking an electrophile, and we saw what those things were in the last video. So here we have a nucleophile, which is a bromide ion. It has 4 lone pairs. One of those lone pairs is going to attack this electrophile, which is a carbocation. So it's usually easy to tell the nucleophile. It's either going to have a lone pair or it's going to have a negative charge. Okay, so it's pretty easy usually to pick that out. The electrophile may not always be so obvious, but it's going to have a partial positive or a positive somewhere. So we put the tail of the arrow on the lone pair, and then we draw an arrow to where it is going, in this case the positively charged carbon. So that lone pair is becoming a bond between the carbon and the bromine. So that lone pair has become this bond right here. Now what we don't do is draw atoms flying off into space. So like for example, let's go back up. We don't draw this hydrogen flying off into space somewhere, okay? Or even we don't draw the hydrogen going over there. Since the hydrogen went here, some students are going to draw the hydrogen going over here. These arrows are not showing where the atoms are going. What they're showing is movement of electrons. So we put the tail of the arrow where the electrons are coming from, the head of the arrow on where the electrons are going. And you need to be very specific with this in Wiley Plus or in your exam if you're drawing this. Okay, so nucleophilic attack may require more than one curved arrow, especially if you end up with too many electrons around your carbon or whatever it's attacking, so around where your electrophile is. And so we have the nucleophile on the left that is an alcohol. It has these 2 lone pairs, so one of them can attack as a nucleophile. So this oxygen of the nucleophile is attacking the carbon of the electrophile. Remember, this one is partial positive, right? So that we put the tail of the arrow on where the electrons are coming from, the head on where those electrons are going. So we formed this bond right here between the carbon and the oxygen. Okay. Now, when we do that, we end up with too many electrons around that carbon of the carbonyl, and so the pi bond between the oxygen and carbon of the carbonyl is going to become a lone pair. So we draw the tail of the arrow on the pi bond, the head on the oxygen where it's going. So this pi bond becomes a lone pair, and here is the lone pair that was the pi bond, okay? So it took 2 arrows to effect that step. Now, the alcohol is going to attack the carbon that has a partial positive charge. That's because it's the electrophile, and the alcohol is acting as a nucleophile because it has that region of high electron density, those lone pairs. Now, remember we drew resonance structures previously where we could show that a carbonyl could have another resonance structure because we have a pi bond between 2 atoms of differing electronegativity. So we can draw that pi bond becoming a lone pair up on the oxygen, okay, and so that would turn that carbon into a carbocation in the second resonance structure, which may be a better representation for this mechanistic step. So if that carbon has a positive charge, it's very clear that it will act as an electrophile, and then the alcohol can attack it. So we put the tail of the arrow on the oxygen, the head on where it's going. So we formed a bond between that oxygen of the alcohol and the carbon of the carbonyl. So notice that the top step and the bottom step are showing exactly the same thing. They're just showing it in 2 different ways. So you can show the oxygen attacking the electrophile first and then the pi bond becoming a lone pair, or you can show the pi bond becoming a lone pair first and then the oxygen attacking. So to get these mechanisms down, it's really good to just do them over and over. So if we study, say, the SN2 mechanism, just practice doing that mechanism over and over with some different examples, and it'll become pretty clear how to draw that mechanism. And teachers usually have a preferred method for doing this. Some teachers will use the top method, some will use the bottom method. Your book generally uses the top method, and so that's the one that I'm generally going to use. I usually follow that top method. Okay, so nucleophilic attack also can be done with pi bonds acting as nucleophiles. So here we have a pi bond from a benzene ring, this aromatic ring. So there's a large region of electron density all the way around this ring. So one of these pi bonds is acting as a nucleophile attacking this sulfur. And so we show this pi bond between the sulfur and oxygen becoming a lone pair. Okay, so pi bond forms a bond to the sulfur right here. Okay, so the tail on the pi bond, the head on the sulfur where it's going. Then the sulfur-oxygen bond is broken, the tail goes on the pi bond, the head goes on where it's going. And so it ends up as a lone pair. So you may ask yourself, how can I predict this? Well, like I said, just practice, do these reaction mechanisms over and over, because each mechanism that we're going to study, and even those that you're going to be studying in the second semester, whether you have me for a teacher or someone else, the teacher is going to go over a specific mechanism, and you can work different examples of that mechanism and learn these steps. So you don't have to usually predict how this is going to happen. You're going to know how the mechanism occurs, and then you just practice it. Okay? All right, and so next we have loss of leaving groups. So this is the other way electrons can move in a mechanism. So the first one was nucleophilic attack. The next is loss of leaving group. Okay, so here we have a heterolytic bond cleavage where an atom picks up and leaves and takes its bond with it as a lone pair. It takes the electrons that were in the bond away as a lone pair. Okay, so this bond between the carbon and bromine is going to be broken, where this bromine picks up and leaves and takes the 2 electrons in the bond with it. So it's taken those electrons away as a lone pair, shown on the right, and it leaves behind the carbocation from the carbon that it was attached to. So now we have this carbocation, okay? And so that only shows one arrow, so we can just show one arrow with that loss of leaving group, and that's often true. Now, on the right, we have a specific example where we have a nitro group, okay? And this looks really scary. I really don't like to introduce the nitro group so early in this course, but it's being introduced because we will see it in one specific place in the second semester of this course, and that is with a nucleophilic aromatic substitution mechanism. So the nitro group plays a key role in the nucleophilic aromatic substitution mechanism, which is abbreviated SNAR. Okay, and so that's why this is being shown. But we can see an example of how the flow of electron density can just keep going all the way through a molecule, allowing a mechanism to occur. So I don't want my students to worry too much about this right now. But here we formed a species where this nitro group has two negatively charged oxygens. One of those is going to, one of its lone pairs is going to become a pi bond. So the tail is on the lone pair, the head is on the pi bond. Okay, when that happens, then we've got this nitrogen that's double bonded to a carbon. That pi bond is going to move. Now we've got too many bonds around this carbon to its left, and so that pi bond is going to move here. And then we've got this carbon-chlorine bond that's going to become a lone pair on the chlorine, kicking the chlorine out. So this movement of electrons shows the removal of that chlorine in the end. And that, again, that step will be demonstrated in nucleophilic aromatic substitution in semester 2. All right, the next mechanistic step that we'll study, remember there are only 4 of them, is a proton transfer. And this looks kind of like a nucleophilic attack in that we have a lone pair that's going to attack a partial positive. Remember there's a partial positive on this hydrogen right here, and so it's going to pick that hydrogen off. So that's a proton transfer. So lone pair, the tail of the bond is on the lone pair, the head is on the hydrogen where it's ending up, and so we formed this oxygen-hydrogen bond on the right. And then we have a second arrow between the oxygen and hydrogen of the acid. The bond is on the tail is on the bond, the head is on the oxygen where it's going, okay? So we end up with water as our second product, okay? So that's just not shown. All right, and so sometimes that's shown with just a single arrow. Comparing this, the deprotonation step, where we're going to pull that hydrogen back off. So this is a reverse, is also a proton transfer. So water picks up a hydrogen. In other words, this reaction on the top is reversible. So here on the left, we're showing water picking up a hydrogen. And when it does, then the oxygen-hydrogen bond is being broken, and that bond becomes a lone pair. So the reaction, that reaction is reversible. And so we get back out our starting material here. That was up here, right? Okay, and so some books will show just that hydrogen floating off into space and the bond becoming a lone pair and just saying minus H plus because that hydrogen was lost. They consider proton transfers to be so insignificant that that step doesn't need to be shown. And a lot of times it isn't shown in different books because hydrogens do, if they are acidic, they do in fact float around in the solution and they're transferred to many different things in solution. But this is not a technique that your book uses, and it's not a technique that I use either. So this on the right, this method of showing a proton transfer would never be done in this course, and it won't be done in your book. Okay, so there are many different types of proton transfers, so lots of different compounds can be acidic. Here we have a carbon next to a carbonyl being shown as acidic, so this hydroxide is going to remove that hydrogen, and so when it does, then the bond between the carbon and hydrogen that existed is being broken, and that bond is actually becoming a pi bond over here, which is going to force the next pi bond to become a lone pair to be broken and become a lone pair. Okay, so that actually requires 3 arrows. So that might be a little bit confusing, but, and like I said, you're going to memorize these mechanistic steps. It's not going to be something that you're going to have to predict, okay? So generally, your book is going to draw that particular step as is done down here on the bottom left. This lone pair is going to pull a hydrogen off, and then that bond is going to become a lone pair on the carbon. Then we can draw a resonance structure from that, a carbanion. The lone pair becomes a pi bond, the pi bond becomes a lone pair. And we won't see this mechanism until the second semester of this course. So remember, there are 4 mechanistic step possibilities. The 4th one is a rearrangement. So carbocations can do what's called rearrange. So this is kind of unintuitive for new organic chemistry students. So the reason this happens is because carbocations can be stabilized by neighboring groups through orbital overlapping, and this is called hyperconjugation. So we have this carbocation here on the left, and this carbon has this empty p orbital. That empty p orbital is missing 2 electrons. That carbon is electron deficient. It only has 6 electrons around it. And so it wants to be stabilized by something. And so we have this methyl group next door. That methyl group can orient itself so that the carbon-hydrogen sigma bond, one of the carbon-hydrogen sigma bonds, aligns itself with that empty p orbital. And it can donate electron density into that empty p orbital to stabilize it. So in fact, we're going to see in the next chapter that carbocations that have more alkyl groups around them are actually more stable and more likely to form, and this is the reason for that. But there's also another possibility, and that is that these alkyl groups can actually pick up and move in order to fill that void, to fill that empty p orbital that has formed on the carbon, on the carbocation. So what happens is the alkyl groups move, and this can be very frustrating to new organic chemistry students. Okay. So the trend for hyperconjugation is explained by the stability of the carbocation. So the methyl group is the least stable, and then if we have 1 alkyl group, that's called primary, because it has 1 alkyl group, so primary. And then we have a carbocation possibility that has 2 alkyl groups, that's called secondary, okay? And 3 alkyl groups is called tertiary. Well, a tertiary carbocation is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl, okay? And so increasing the substitution of the carbocation increases the stability, and that is going to allow those neighboring carbons to align themselves with that empty p orbital. And what happens then is that the whole molecule can rearrange. So in fact, it can rearrange in many different ways, but the primary ways that we see is through a hydride shift, or at least in the early years of studying this, a hydride shift and a methyl shift. Okay, so we can get a hydride shift, so that hydrogen, this carbon that has maybe a hydrogen, maybe 3 hydrogens, or maybe just 1 hydrogen, that hydrogen can align itself. Remember that empty p orbital. That hydrogen, carbon-hydrogen sigma bond aligns itself with that empty p orbital, and then when it aligns itself with the empty p orbital, it can allow this bond to shift over and fill that void, and that whole hydrogen can then just be shifted. Now, it's called a hydride shift because a hydrogen with the 2 electrons, well, let me rephrase that. A hydrogen with 2 electrons and a negative charge is called a hydride, okay? But notice that this hydrogen is taking the 2 electrons in the bond with it, and that's why this is called a hydride shift, okay? Because it comes from that term for a hydride, which is a hydrogen with 2 electrons. Okay, so what happens then, now that this carbon on the left has lost its hydrogen with its 2 electrons up from the bond, it has become now positively charged. Okay, so why is it positively charged? Let's change our colors here. Remember, the hydrogen over here had 1, 2, 3 bonds, right? And so carbon wants 4 electrons. This carbon owns half the bond, so it's got 3, so it's short an electron. So that gives it a +1 charge. Now this carbon on the right owns half the bonds, and so that it wants 4 electrons. It owns 3, so that leaves it with a +1 charge. Okay? And the next thing we have is, usually this is called a methyl shift. I don't know why it's being called a methide shift here, but normally this is called a methyl shift. And so what happens here is this carbon has aligned itself, okay? So the carbon-carbon bond now, instead of the carbon-hydrogen bond, sigma bond, has aligned itself with that empty p orbital. And so that whole carbon then can be shifted over. The entire methyl group gets shifted over, and that leaves the positive charge behind on the other carbon, on the neighboring carbon. So why does this happen? Because notice that this on the top, this carbon here had 2 other carbons attached, so it was secondary. When the positive charge shifts over, when the hydrogen shifts over, it shifts the positive charge to the neighboring carbon. Now the carbon with the positive charge has 3 carbons attached. 1, 2, 3. So now it is tertiary. Okay, so the same thing with the methyl group. The positive charge was on a secondary carbocation, and now the positive charge ends up on a tertiary carbocation. It has 3 carbons attached. Okay. So these shifts only occur if a more stable carbocation results, and in fact these are the only ones that we study generally in this course, but all kinds of alkyl shifts can occur. It doesn't have to be just a methyl shift, it can be an entire R group of some sort. You can get a shortening or a lengthening of a ring, or just all kinds of different things can happen in real life. Alright, so for each of the following cases, let's read the curved arrows and identify which arrow pushing pattern is utilized. Okay, so here we have a carbocation, and that could be a key to look for a rearrangement. This hydrogen is moving over, so we get a hydride shift, so that is a rearrangement. Now, it might not be so clear because you're not seeing the hydrogen where it moved. This is kind of an unclear example, but there are 2 hydrogens here now where there was only 1 before. Okay, so that was a rearrangement. On B, we've got an oxygen attacking a carbocation. So what is that? That's not a hydride shift, okay? It's not a proton transfer, so it has to be a nucleophilic attack. So what were our steps? Let's remember, we've got nucleophilic attack, proton transfer, what is it? Proton transfer, nucleophilic attack, rearrangement. What's the third one? Loss of leaving group. Okay. So we can have any of these 4 steps in our mechanism, right? So for C, we've got this oxygen. It looks like a nucleophilic attack kind of, but it's going over to this hydrogen, and the hydrogen is being lost, okay? So this is a proton transfer. People get confused on these hydrogens because it looks kind of like a nucleophilic attack. It also kind of looks like a loss of leaving group, but when it's the hydrogen that's doing the leaving, it's a proton transfer. Unless it's a rearrangement where it takes its electrons with it, but then the bond wouldn't be broken between the carbon and the hydrogen, okay? The next one, we've got an oxygen attacking this carbocation, so this is a nucleophilic attack, okay? And the next one, we've got a chlorine taking its 2 electrons with it from the bond, and so that's loss of leaving group. Okay? So those are our possible steps. Now we can combine these steps into more than one step. Okay, so here we've got an entire mechanism. Okay, so first we have a proton transfer, then we have a loss of leaving group, then we have a rearrangement, then we have a nucleophilic attack. And we're going to see mechanisms that have all of these steps in them over and over. Sometimes we'll just see one or two steps, but oftentimes we'll see all of them or many of them. And so sometimes they can occur in a single mechanistic step, such as this right here, where we've got nucleophilic attack and loss of leaving group at the same time. So for each of the following multi-step reactions, let's identify the sequence of arrow pushing patterns. So for A, we've got nucleophilic attack, then we've got proton transfer, then we've got another proton transfer, okay? And then for B, we've got proton transfer, then we've got nucleophilic attack, then we've got, let's see, this is a loss of leaving group. So we've got nucleophilic attack, loss of leaving group. Okay, so here for C, we've got proton transfer, then we've got loss of leaving group, then we've got nucleophilic attack, we've got proton transfer. Okay, so next we've got proton transfer, then we've got nucleophilic attack, then we've got, let's see, proton transfer. Okay, so that's that. All right. We've already talked about this. To draw the curved arrows, we can show a lone pair becoming a bond and a bond becoming a lone pair. Okay, so we want to put the tail on where it's coming from, the head specifically on where it's going. So the one down here on the bottom is drawn incorrectly. Normally I'm not going to put just a negative charge. Some teachers do that where they'll put the tail on just an atom that has a negative charge. The head is going to the carbon where it's going, but this carbon is shown as going off into space, which is not what's happening. So the second arrow is wrong. What we want to do is show the bond becoming a lone pair on that chlorine. So what's our product here? I mean, we're not going to study this reaction right now, but this would be actually the product. It's 2 carbons, okay? Plus Cl minus, right? All right, so the head, the head of a curved arrow shows either the formation of a bond or the formation of a lone pair. So lone pair becomes a bond, or bond becomes a lone pair. Sometimes we show bonds moving, stuff like that, or lone pairs moving. Okay, so you can't show a carbon forming more than 4 bonds. We talked about that a little bit because you're going to have too many bonds to carbon. Okay, so you've got to show, if you're forming a bond, you got to show something else leaving if it's going to give you too many bonds to carbon. So any curved arrow that you draw should describe one of the 4 patterns discussed. So we've got nucleophilic attack, loss of leaving group, okay? And it needs to kind of make sense. So this one doesn't, because there's really nothing to attack over here. There's no leaving group, so the pi bond can't attack that carbon over there. It doesn't make any sense. So let's practice drawing curved arrows that accomplish these transformations. Okay, so what did we do going from left to right on A? We've got a carbocation here, and from that carbocation we formed a bond to the oxygen. So that's what happened. So how do we draw that? One of the lone pairs on the oxygen is attacking that carbocation in a nucleophilic attack to form this bond. Okay, so for the next one, what did we do? This carbon-oxygen bond is right here, and what happened was it lost a hydrogen. Okay, it lost a hydrogen, so that was a proton transfer, so it had to have been picked up by something acting as a base. So water, the oxygen is acting as a base, picking up the hydrogen, and then the bond between the oxygen and hydrogen is being broken to become a lone pair. So that's how you draw that. Okay, So the next one is this water has come away from the carbon that it was attached to. Okay, so that is a loss of leaving group, and we've left behind the 3 carbons that were attached to that central carbon, forming a carbocation there. So that bond has become a lone pair on the oxygen, leaving the carbocation behind. So that just takes 1 arrow. So remember to consider carbocation rearrangements whenever that could result in a more stable carbocation. So let's consider this one. We've got a secondary carbocation because this carbon in the center has 2 side carbons. It also has a hydrogen that's not shown because it has a positive charge. Now, could it be more stable if something next door moved? For your purposes, you only look 1 carbon over. So 1 carbon over, we've got a hydrogen. If we move that, it's not going to be more stable. Okay, and if we move to the right, okay, we've got hydrogen and methyl. Okay, if we move the methyl group over, then what's that going to give us? It's going to give us the methyl group here, and the hydrogen that was there is still there. Now we've just got, oh no, I moved the wrong thing, didn't I? Okay, let's do this one again. Sometimes you got to sit and think about it a minute. So the question is, what would result in a more stable carbocation? So going back, we had a hydrogen on that carbon and 2 other carbons. So we're looking to form a tertiary carbocation there. Okay, so the carbon next door on the left just has 2 hydrogens. If we move a hydrogen over, we're not going to have a more stable carbocation. But this carbon over here on the right has a methyl and a hydrogen. What happens if we move this methyl over? Okay, then that's going to put the hydrogen over here. Where does that leave the carbocation? That leaves the carbocation right here. So the hydrogen that was right here moved over to this carbon, okay, taking its 2 electrons with it, so with a hydride shift. And now that puts a positive charge on the carbon next door. Now this carbon is tertiary. All right. So tertiary carbocations generally don't rearrange unless you can form something that's resonance stabilized, which will be more stable. So tertiary is about the same stability as allylic, but if you can form an allylic tertiary carbocation, that's even more stable. So here we have this hydride shift that's occurring because then we can put the positive charge on this carbon that now is allylic, and we can draw a resonance structure. So remember, resonance structures add stability. Okay. So for each of the following carbocations, let's determine if they will rearrange, and if so, draw the rearrangement with a curved arrow. So I may not draw all of these out, but this, for A, we have a carbon and hydrogen next door to the carbocation. So if we move a hydride over, what do we get? We get, now we have 2 hydrogens on that carbon and a positive charge here. Now it's tertiary, it was secondary. Okay, so this one's more stable. So what about B? B is already tertiary. Okay, so generally it won't rearrange unless it can be more stable, like allylic. So for C, what do we have? Okay, so for C, if we move one of these methyl groups over, we end up with the positive charge here, and the methyl groups are now over here. So now we've got tertiary allylic. Okay, so we can draw a resonance structure. Let me get a different color. We can draw a resonance structure for that molecule that distributes the positive charge to the next carbon. So because it is has resonance and is still tertiary, it's going to be more stable, so it will rearrange. Okay, I'll let you guys work some of the rest of those. Okay, I'm going to go ahead and finish this chapter because we only got a couple of slides left. So let's talk about reversible and irreversible reaction arrows. Actually, I think I'm going to go ahead and stop here and make another video for this.